Welcome, ladies and gentlemen, to a lecture on solving problems using rotational dynamics. What I'd like to do today is just solve some example problems to help us get a better idea of how we use these tools for solving problems. So our first example. Consider a hockey puck that is propelled along the ice into a waiting net that is on the end of a long pole. The pole is anchored to the ice on one end, but is free to rotate once the puck is caught in the net. What will the angular velocity of the contraption be after the puck is caught? So what we have is a pivot right here. Okay, that's going to be our axis of rotation. We have a long stick, and we have a net on one end. Okay? And then we have a hockey puck. It's got some velocity v, and it goes into the net. The net is going to have this distance r, okay? And then, of course, the hockey puck at any point along this is going to have this distance r, okay? From the center of mass of the hockey puck to the pivot. So if we start on this one, if we look at the angular momentum of the hockey puck, when we're starting, that's r cross p, right? Which is r cross mv, which is mrv sine theta, where theta is the angle between r, which points like this, and v, so it's this angle right here, right? But if I look at my triangle here, notice that what I have is a right angle right here, right? I have a right triangle, and so this across from the angle here, this side that I've marked capital R, that's actually r sine theta, right? So this becomes m big R v. Okay? And this is something that we see regularly when we're using conservation of momentum. If we take and have this velocity moving, if we go to the point where it's perpendicular to the axis of rotation, that's always going to end up being the piece that's distilled out of our cross product. So this radius that I marked r for the system, that's always what we're going to end up having here in the angular momentum for something that is moving like a particle with respect to some axis. Okay, the puck is just moving like a particle with respect to this axis right here. Okay? And then we need to think about the angular momentum for the different pieces. Okay, so if we have I for the net, remember for some object like this, we can take the center of mass, and presumably the center of the mass of the net is along this dotted line somewhere. Okay? And then we can treat it as if all the mass is right there. Okay? And to do that, as long as... Sorry, let me be clear about that. We can do that as long as this distance, the kind of size of the object, is very small compared to this distance r. Okay? And the net presumably is pretty small compared to that distance. So we can make this approximation. So for the net, we can say that we have the mass of the net times r squared. Okay? The location of its center of mass with respect to the axis of rotation, and the mass of the net. Okay? And then for the stick, we have this whole extended object rotating around, and let's call the length of the pole here L. Okay? Then if I look up in a chart of moments of inertia, I'll see that for a stick like this, I is 1/3 m L squared. Okay? Okay, so now what we're going to do is use conservation of angular momentum. That says L initial equals L final. Right? That's it. So what is L initial? Well, initially the only thing moving is the puck, and we found this angular momentum of the puck, and it's mRv. Okay? And then final, we have in omega. Okay, it's going to have some angular velocity. Plus I of the stick, omega. Plus, and then we have the mass of the puck, m, and r squared. It'll be in the middle of the net here. Okay, so it's going to have this mr squared for an I, and then of course omega, just like everything else. Because once the puck is in the net, everything is spinning together. Okay, so the omega of every part is going to be the same because they're all just kind of one thing now that's spinning around this axis. So then that means that mRv equals in plus is plus mr squared omega. And then we plug in for each of these things. So in is mass of the net, r squared, plus, and then is 1/3 ml squared. Let's put an s on these m's to make it clear that's the stick, okay? Plus, and then the mass of the puck is what we're using just m for, right? mr squared omega. And then that tells us that omega equals mRv. Man, I'm having a hard time writing on this thing today. mRv over mn r squared plus 1/3 ms l squared plus m r squared. Okay? And that's going to be our angular momentum for the end. And the only thing that was really important to this whole thing was just that we were very careful about accounting for every piece of angular momentum here at the end. Okay? In the beginning, it was really easy. The puck was the only thing moving, so the puck was the only thing with angular momentum. And then we just have to be really careful, make sure that we are methodical about grabbing every single piece of angular momentum that's there at the end, and we just add them all together, and we have angular momentum. Okay? Now, these are vectors, but I was able to just add these things without breaking them into components because everything's going to spin around this same axis. Okay? So I took care of the vector part by finding the angular momentum of the puck in the beginning with respect to this axis, okay, and in this direction, right? And then at the end, everything is together spinning in this direction around this axis, okay? So the component part of it was taken care of by the fact that I was already finding things spinning in this direction, okay? So we can't generally just add things like this unless we're already taking care of the vector part of it by getting everything in reference to the same axis and the same direction. Okay? So now let's look at example 2. Recall that we considered a car rolling down a hill as sliding without friction in the past. How far off was that approximation? So this is something we might be curious about, right? Before, we said, if a car's rolling down a hill, the wheels are pretty small. Let's just say it's sliding without friction. Okay? Well, that, of course, is an approximation. It's not sliding without friction, right? It's rolling down the hill. So how far off is that approximation? How much error did we introduce into our answers by making this approximation? Okay? So to do this, I wanted to take some kind of common car. So I took a Toyota Corolla. Okay, it's one of the most common cars out there. And that car has a mass, m, of 1383 kilograms. That's the curb weight that I found, okay? So that's the total mass for the car. That's including the wheels. I assume it had fluids in it. No idea, okay? The whole car. Now, for wheels, for the mass for wheels, that was a lot harder to find. But what I found was that for a 17-inch wheel plus a tire, we could expect a mass for the wheels of around 20 kilograms. Okay? And then if we have some round object, if you notice, if you go look in the table of moments of inertia, they usually look like this, right? C, M, R squared, where this is R, right? And this constant is what changes from object to object, right? It's some number. But if you notice, that constant is always less than 1, except for something that's a real thin ring, okay? Now, technically, it has to be an infinitely thin ring for it to be truly 1. But if we have a really thin ring like this, then we kind of approximate it as an infinitely thin ring, okay? And we say that this C is 1. So we just have mr squared. And that's kind of a worst case scenario for moment of inertia, okay? And so that's what we're going to use for the wheels, okay? So assuming that the wheels have all the mass around the edges, and that's not bad for a car wheel, right? There's usually some little spokes in here, and there's some thickness to the tire, but we do kind of have all the mass around the edge, right? So this isn't the worst, but it is definitely making the most conservative assumption, okay? All the mass is around the rim. We're making the moment of inertia as big as possible, which means that as much, this is kind of the most energy that could be sunk into rotational energy of the wheels. So we have this kind of conservative assumption for our moment of inertia. And then when we look at the problem, what we generally had was our little Toyota Corolla up here, right? And it was some height, Y, and it rolled down to the bottom of the hill. Okay, so let's start this by first, up here as a little aside, doing it for sliding without friction, okay? So if we solve this problem with sliding without friction, of course we're going to use conservation of mechanical energy to solve this problem, right? And so we have U initial plus K initial plus work non-conservative equals U final plus K final, okay? And remember, for sliding without friction, we just have gravitational potential energy at the top. At the bottom, all that gravitational potential energy is gone. And we have translational kinetic energy, right? And let's call this V1 for this. And then we find that V1, okay, V for sliding without friction, is 2gy in a root, okay? So now let's look at it for rolling without slipping down the hill. In the beginning, of course, we still just have gravitational potential energy. And then at the end, what's different is that now we still have the translational energy of the car, right? But now we also have this rotational energy of the wheels, okay? 1/2 I omega squared. So some of our gravitational potential energy got used up to give the wheels rotational kinetic energy. And then we still, of course, have the kinetic energy of the whole thing, the wheels and the car and the whole bit, right? And then for this, I'm going to multiply by 4 because I have 4 wheels, okay? And each one of those wheels is going to have this kinetic energy, okay? This rotational kinetic energy. The translational kinetic energy of the wheels is bound up in this, okay? Because the mass, this big M, this includes the wheels. Okay. So then I just leave this alone for the moment. I have plus 4 times 1/2. And then we said we were going to have I be mr squared, right? Our most kind of conservative case. And then the omega for rolling without slipping is V over R, okay? And then that's squared. And so then what we end up with is 1/2 m v squared plus the 4 and the half go together to make a 2. The r squared's canceled, and I get mv squared. okay? And then if I multiply the whole thing by 2, I'll get 2 big M gy equals m v squared plus 4 little m v squared, okay? And then that tells me that v equals 2gy from this left side, right, times big M divided by big M plus 4 little m. And that's all in a root, okay? So the reason that I simplified it this way, you can probably see now, is because I have this 2gy, right? And that was the sliding without friction. And then I have this other term that just modifies my answer, okay? So I have my main answer, the sliding without friction, and then I have this little piece that just perturbs that answer, right? It adjusts it, makes it a little bit more realistic. So then if I wanted to compare these two answers, okay, a good way is to take a ratio. And if I have v over v1, then what I would have is, of course, 2gy over 2gy. Now, both of these velocities, the thing on the right is in a root, right? So in the end here, I'm going to put this whole thing in a root. But if I have the numerator and the denominator both in a root, I can just put the whole fraction in a root, okay? So that's what I'm going to do. So I have the 2gy from this one, and I have the 2gy from the sliding without friction. And then, of course, I also have this term for the car rolling down the hill, okay? And then that equals m over m plus 4 little m in a root, okay? And so v equals m over big M plus 4 little m in a root times the speed that we have for sliding without friction, okay? And again, this goes back to what I pointed out when I found the answer. The answer is the answer for sliding without friction plus some perturbation, right? Plus some little change that comes from the fact that the wheels were rolling, not sliding without friction, okay? And then if we do this, we find that v, if we plug in these masses, equals 0.97 v1, okay? So when we made the approximation that a car rolling down a hill was sliding without friction, we were only off by about 3%, okay? When we solve it with the wheels rolling for this kind of realistic case with the Toyota Corolla, okay? The mass here is the Toyota Corolla. And for this conservative moment of inertia for the wheels, we find that we were off by about 3%, okay? That's actually not bad, right? 3% isn't so bad. And it made the problem very quick for us to do that, right? Now, depending on the car, if the Toyota Corolla was much heavier and the wheels were the same, we'd be off by even less, right? Or if we had a truck that was a little heavier than the Toyota Corolla but had great big tires that were way heavier than the Toyota Corolla, then we might be off by a little bit more, right? Because in the end, how far we're off by depends on this, right? So the mass of the car and the mass of the wheels are both going to affect how far we're off in this approximation, okay? But in general, for just kind of a normal car and some normal wheels, 3% is not too bad. Okay, and then this last one is a little bit more textbooky example, okay? So if a uniform density disk with a mass of 1.65 kilograms and a radius of 15 centimeters has a constant torque of 650 newton meters applied to it, how much time will it take for the disk to be spinning at 1,000 RPM? Okay? So this is kind of like maybe a small flywheel being spun by actually a pretty big torque. Okay, so we have a pretty good sized torque here. So we have our wheel here, radius r. It's spinning like this. We have that torque equals 650 Newton meters. We have a mass equal to 1.65 kilograms. We have a radius equal to 15.0 centimeters. And then we're going to have a final angular velocity of 1,000 RPM. Okay? And then it wants to know t equals what? Okay? So the first thing that I can do here, because I'm going to be finding time, I can change this angular velocity. Well, not just can, I should change this to radians per second. Okay? So WF equals 1,000 revolutions per minute. And that's 2 pi radians per revolution. Right? And 60 seconds per minute. And then what I get is that we'll just replace this. This 1,000 RPM is 104.72 radians per second. Okay, and then what I want to use to solve this is that torque equals I alpha. Okay? They didn't really tell us what direction torque is. I just picked a direction it's spinning. Okay? And of course, whatever direction the torque is, that's what direction the angular acceleration is going to be. Okay? So for a solid disk here, we'll have I equals 1/2 m r squared. Okay? A solid disk is really just a solid cylinder, right? If you're looking at a chart of moments of inertia, it's a solid cylinder where the height of the cylinder is really, really small, right? That's all a disk is, or a ring, right? A ring would be a hollow cylinder where the height is really, really small. So then over here, we'll just apply what we said. Tau equals I alpha equals 1/2 mr squared alpha. Okay? So therefore, alpha equals 2 tau over mr squared. Okay? And then we're going to apply the tool of kind of the rotational analog of kinematics. Okay? So we're doing rotational kinematics, and we have omega equals omega naught plus alpha t, right? That's that v equals v naught plus at, but now I've just replaced everything with its kind of angular analog, right? Omega naught is 0, and so what we end up with is omega equals alpha t, okay? And therefore, t equals omega over alpha. And that means that t equals omega mr squared over 2 tau. You can see if you check this that our units work. Okay, I'll leave that to you guys. For sanity checks, T decreases as the torque goes up. Okay, that makes sense. If I want to spin it to some particular RPM, the bigger torque I apply, the faster I'll get it to that RPM. Okay? T also goes up as omega, M, or R go up. So if I have the same torque, if I'm not changing the torque, if I want to make it spin to a higher RPM, it takes longer. That makes sense, right? You can see T goes up as M goes up. So if the wheel has more mass and I apply the same torque, it'll take me longer to spin it up to some given RPM. That makes sense as well. And then also, as the radius goes up, the time goes up. And again, if I make the wheel bigger, then I'm moving some of the mass further away from the axis of rotation, right? Making its moment of inertia bigger, which means that it resists changes to its angular velocity more. So that makes sense, okay? It'll take longer if I apply the same torque to a bigger wheel to get it spinning as fast, okay? And then for this, if we plug in the numbers, I think what we find is that we have 0.000299 seconds. So what we have ultimately is a wheel that doesn't weigh very much. We apply a great big torque to it, and so we spin it up to 1,000 RPM almost instantly. So that concludes our lecture for today. These examples, along with your homework, should be helping you to get a handle on the concepts involved in rotational dynamics, and we'll do some more examples in the next lecture.